Good evening, folks. I'm Rohini. I work for the Hadoop team at Yahoo. Today I'll be co-presenting on Pig 14 with Daniel from Hortonworks. So, both of us are Pig committers and Pig PMC, and we have been leading the effort for Pig 14 along with Shalsu from Netflix. Both of us are here, it's Daniel and Shalsu. So today we'll be talking about Pig 14, what's the major features, other usability and performance improvements that have gone in. So Pig 14, actually the voting closes today and it will be released tonight. Daniel is a night owl, so he's a release manager, so most likely you would get it later tonight or tomorrow morning, not sure which. So we have 226 GRs resolved, we have 35 contributors, in fact we have a lot of new contributors and a lot of GRs contributed by the new folks. So special thanks to all of them. And the major contributions came in from Hortonworks, Yahoo and Netflix. So we were also working very closely with Taste community because the major feature in this release was Pig on Taste, and we needed a lot of new features in Taste. And in fact, we drove most of the requirements for Taste along with Hive. And also we had, Taste had to undergo a lot of design changes because of the requirements of Pig. If Taste folks are here, thanks a lot guys. It has been really great working with you folks. So early adoption. So in Apache, we are releasing it today, but Shalsu had it deployed in Netflix just last week. And we rolled out it in Yahoo and Sandbox clusters today, and it's going on research tomorrow and production next week. So as is customary, we always have two versions of Pig and let users migrate slowly to the new one. So the new release, we are starting with Taze as the default mode, and we're not going to support MapReduce with Pig 14 Taze in Yahoo. So Pig on Taze. So the primary goal of Pig on Taze, at least for us, is performance. So with big data analytics getting bigger and bigger, and you want like lesser response times and ETL to be way faster. So performance is one of the primary goals. The other is reduced resource usage. So the cluster capacity in terms of memory and CPU is limited. So instead of adding more and more capacity, what we want to do is do things more efficiently so that we can run way more things using less resources. It's not, supposed to be commodity hardware and takes a lot of money to upgrade memory, CPU, get new nodes. Okay, talking about features of Pig on Taze. The first thing, our first goal was to have Pig on Taze to production quality. We want it to be fully stable, fully feature compliant with MR, and when you run it, what we wanted was like you just introduce -x Taze, which is the execution mode, and we wanted the existing Pig scripts to run fine, so that users don't have any effort in migrating to a new platform or new framework. So all that investment that Yahoo had put in, there are like millions of Pig jobs that run in Yahoo every month, and around 60 to 70% of the ETL jobs are Pig jobs. So that's one of the reasons we wanted to get Pig really fast, and we didn't want anything else to change. We didn't want the scripts to change, we didn't want the settings to change, we didn't want users to recompile any of their UDFs or any load func or store funcs. So that's one of the things that was the top on our list, to be fully stable and of production quality. So there are few features, only two features that is actually missing from compared to MapReduce. We don't have Illustrate, which is a very not so used feature in Pig, which is used primarily for debugging and testing. And there's a local mode with MapReduce, which is again used for local testing before you run it on the cluster. So Taze has a local mode, but it's kind of experimental now and not so stable. But other than that, it's fully feature compatible with MapReduce. So prerequisites, you need a Hadoop 2.4 plus cluster, and you need to have Taze deployed on HDFS and have a Taze site XML telling where Taze is deployed on HDFS. So the setup is very pretty simple and easy. So that's Pig on Taze execution in a nutshell, usage and execution in a nutshell. So going to the design. So what we have done is we didn't want to disturb the code base much. So Pig used to have the logical plan generated when it passes the Pig script, And from the logical plan, we used to run a lot of optimizers and create a physical plan, which would then be split into multiple MapReduce jobs and an MR plan created and executed with an MR execution engine. So what we did is we created a fork here, take the physical plan, but we had to make a lot of changes to the physical plan as well, introduce new operators to work with Taste, and we created a Taste plan and then we executed with a Taste engine. So probably I should have given an overview about Taste first. Sorry, I missed that. So Taste is a DAG execution engine. If you haven't heard about it or attended any of the talks on Taste, I think there's a talk after this which might go more in detail. So I'm not going into the benefits of Taste or like how great Taste is and all that. So how it differs from MapReduce and Taste. So this is like a side-by-side comparison of a big job on MapReduce and on Taste. So we have a script where you load data, perform two group bys, and do a join. So pick tries to be as smart as possible. Usually you would have to have one Hadoop job for each of the operators, like group, the first group, the second group, and third group. But pick tries to be smart. It combines the two group bys into one Hadoop job. So you have one Hadoop job loading the data and performing the two group bys. So you still cannot get it done within one Hadoop job, so you store the output to HDFS, and then you have a second Hadoop job that does the join. So in the Taste world, how does it work? So you load the data. So this is one Hadoop job or application, LAN application, if you would call it. So it loads the data. You have multiple vertices and edges connecting the vertices. So it's like a true DAG. So you load the data and you perform two group by operations. So Taste supports multiple outputs and you have multiple inputs and you do the join here. So the plan becomes more simpler. To achieve two group bys in one job, we used to do a lot of multiplexing, demultiplexing, tagging data to say, okay, it's part of this, it's part of that. So all that goes away and it makes it simpler for us. And the other thing is you eliminate the store to HDFS, which avoids a lot of cost. So to actually visualize like how this DAG transforms here. So in case of MapReduce, if you see, you would have a job 1, and this would be the map phase, and you would have n number of map tasks, and this would be the reduce phase, and you would have x number of reducers, and they will store the output to HDFS, and another job would pick it up, and again you would have the same thing repeated. So here in between map and reduce, map writes the output to a local file in each of the node, and the reducers pull the data from the map. So only to talk between two different jobs, you persist in HDFS. So what happens with Taste? So Taste, everything is a vertex. So the map phase, reduce phase now is all, each is a vertex. So you load the data here. Each vertex has a number of tasks, similar to like your map tasks or reduce tasks. And then the data flows in between. So here they write the data locally. And the successor vertices pull data from their predecessor vertices. So, and again, in the next stage, the same thing happens. These write to the local disk and this pulls. So it's kind of a map, reduce paradigm with going down as many levels as you require. You can have complicated DAGs of like any acyclic DAG. You can represent anything with the Taste. So it gives us a lot more flexibility. So since it's not a pig on Taste task and I don't have enough time to delve into all the details on pig on Taste, I'll just give a brief overview of the features that we have used, the Taste features that we have used in pig. So first thing is session reuse. So with session reuse, what we do is you have the yarn applications. You reuse the yarn applications to run more pig scripts. For example, you go to the pig shell, you launch some script, you launch a load or group by, it runs on that, and the next command that you execute runs on the same yarn application. Instead of you launching new job yarn applications every time, it reuses that. That's session reuse. Then you have container reuse. So container reuse is basically you had all these tasks. So let's assume if your cluster had only capacity to run 2 tasks, what would happen is there will be 2 tasks run, and then there will be 2 tasks run. Once these die off, then these 2 would be run. With MapReduce, those 2 are launched totally new. So what Pace does is it reuses its existing JVMs and runs the tasks of these 2 on those. So it saves a lot of time in terms of setup cost. And also the other benefit with that is, probably I should have put it on top, you can do object caching. So in case of things like map site joins where you store the smaller table in memory, so if the same task is being reused, you don't have to load the smaller table into memory again. You can store it in memory and use it. So things like map site joins are really faster. So coming to customized processing. So Pace provides us with a lot of flexibility to do custom processing. So let's go back to MapReduce. So in case of MapReduce, so what would happen is you can write a map function here and you can write a reduce function here. There is always a partitioner, there is always shuffle and sort. So you cannot avoid any of that. So even if you need it or you don't need it, you cannot avoid it. For example, take a simple case of limit. To limit, I actually don't need shuffle, sort. All you need is like you need to limit it. So all that shuffle, sort is going to cost you a lot. So with Pace, everything is like customizable. So I can customize what runs here. I can have my own processor instead of a map or reducer processor, and I can run my own processor there. So the edges, I can define my own edges and own types of input and output. So I can write an unsorted output and consume an unsorted input here. So everything is flexible and customizable. Even the way the data flows in between these edges is customizable. So here it's always a shuffle. Data is partitioned and shuffled to all the nodes. So I can have a broadcast here with Pace. So data from one node is sent to all the nodes. So Pace gives a lot of features and also a lot of flexibility. Pace even gives us flexibility to control how the tasks are scheduled or even to dynamically reduce or increase the parallelism of these tasks. So if we determine that after reducing that the data is reduced considerably, we can, based on the size, it lets us go and reduce the parallelism of the subsequent jobs. So that's what it is customization about. So the vertex processor is like, instead of a map or reduce processor, you have your own processor. You have custom edges between vertices. You can have custom input and output. You can have sorted and partitioned, unsorted, unsorted and partitioned. So you can have all kinds of inputs and outputs. You can write your own. So we have used a lot of these features. We have written a lot of custom stuff to make the algorithms better. So we have written custom vertex managers to better estimate parallelism and change parallelism dynamically. And I already talked about object caching. Then we have vertex groups. So vertex groups is another very good feature in Pace where it lets us group a set of vertices and assume them to combines the output of that and gives one logical input. So in cases like union, it lets us optimize a lot. So that's like a nutshell of some of the features that we heavily use in Pace. So here are some performance numbers. So I have been mostly focused in getting performance numbers for jobs that take a very long time. We haven't been focusing on like jobs that take 3 minutes and trying to get it into run in 1 minute. We have been mostly focusing on getting like 4-hour job to run in like 2 hours or 1 hour, 1 hour job to run in 20 minutes, things like that. So these are some numbers. Scale is something that's very important for us. So we have been trying to run it at with 100K tasks. I even try to run it with 150K tasks. So Pace scales to that extent, but in some of those scripts, we didn't see much performance. So we're working on that to because Pace AM controls, 1 AM controls a lot of tasks compared to MR AM where it's split into multiple jobs. So there's a lot of overhead when it goes above 100K, 150K. So below that we see very good performance. So This is something we'll have to work on and scale. So, yeah, this is like the tasks are really high. So these are just some production scripts. I haven't run any TP series or anything. So the other thing that we have been running is Pigmix. So Pigmix runs on 1 terabyte of data, and if you actually see, you wouldn't see any 5x, 10x, 50x numbers here, because these are run on 1 terabyte and there's no columnar storage involved. So it's just pure difference between the row format, between MapReduce and Taste, and also I think only just 2 scripts even had filter statements in them. So it was mostly all the operations were being performed on the 1 terabyte data. So mostly everything we were able to get like 1.5 to 2.5x. But there were some things that are kind of not so great at this moment, which we will be fixing in the next patch release. So those are order by and merge join. Order by on a lesser data is like pretty fast. Even with this data, it used to give 40% improvement, but with the later patches, it's kind of, we have broken that. We will be fixing it in the patch release. Merge join implementation, we are planning to rewrite it, so that should improve as well. Yeah, so the other thing that we have been trying to do, like going forward, is actually set up TP-CDS with Pig, because we just compare ourselves with Pigmix, so we want to like compare ourselves with the other systems, SQL system, to see where we fared. So that's one thing that we have planned for the next releases going forward. Yeah, that's it with Pig on Taste. I'll hand it over to Daniel to talk about the other features with Pig 14. Daniel.
So, thanks Rohini. He just finished the big feature in Pig 14, which is Pig on Test. But don't forget, we have a bunch of more features other than Pig on Test introduced in this new release. So OrcStorage is one of these. So with OrcStorage, you can read and write Orc file natively from Pig. It doesn't say before that you cannot do that. You can read and write Orc file inside Pig using Edge Cat Loader. But in that, you have to deal with Hive meta store. You have to deal with a Hive table. You are not dealing with the HDFS file itself. So with the OrcStorage, you can read and write Orc file directly. So you don't have to deal with the Hive meta store. And also you have much performance gain, and also you have more features in the OrcStorage. So for those who don't know about OrcFile, so OrcFile stands for the optimized RC file. This is the native data file format supported by Hive. So there's a lot of benefits for the OrcFile itself. I don't want to talk about here. So here I show 2 examples how to use the OrcStorage. So one example is in the load side, and the other example is in the store side. So both are quite straightforward. In the load side, you just load Orc file. This is the Orc file itself. On the HDFS, this is not a Hive table. So you load an Orc file using the OrcStorage. And usually you don't need to separate the schema, because the schema is stored as part of the Orc file itself. So you can load this Orc file using OrcStorage and describe the alias, so you can see the schema of the Orc file. And then you can dump this alias, so you can see the data stored in this Orc file. And on the store side, you can just store the alias into one of the Orc file using OrcStorage. The only thing is you have to give the schema for the alias. Otherwise, OrcStorage will complain that it cannot find the schema. So the syntax for the OrcStorage is very simple. It's just OrcStorage, and it takes one optional parameter, which is the option. On the load side, we don't have any options currently supported. On the store side, we have bunch of options. So you can specify whether you want to use the compression in the Orc file. You can specify the size of the stripe of the Orc file. So all of these are listed in the Pig documentation. So you can easily find the information there. Let's come to the data type mapping. So OrcStorage derived its data type model from Hive. So for most of the primitive type, pig and Hive has a very nice one-to-one mapping. So one pig data type maps to one simple data type in Hive, such as integer, double, floats. There are some exceptions. I listed them in this table. For example, in Orc, you have string, char, varchar, all mapped to char array data type in pig. So if you want to map pig char array back into Orc, it will be the Orc string. And also for the Orc byte and the binary data type, it all mapped to the byte array data type in pig. And if you want to map it back, it all goes to the Orc binary data type. And so on for the rest of 2 items in this table. And for the complex data type, it's also one-to-one mapping. So you have Orc list mapped to take back. You have Orc struct mapped to take tuple, and you have Orc map mapped to take map. And one optimization in OrcStorage is the predicate pushdown. So in OrcStorage, we have multiple levels of stats stored inside OrcStorage. So for every OrcStorage and every stripe inside OrcStorage and every log group inside a stripe, you have the stats such as the min, max for this data block. So use this information, you can immediately get rid of some of the data blocks if it doesn't satisfy some field conditions. So here is how we do the predicate pushdown in pig. So if you have a field statement right after the load statement, we will push this field condition into the OrcStorage. So the OrcStorage will prune the data blocks which doesn't satisfy these conditions entirely. And for those blocks which satisfy this condition, we will have to do the filter again in the pig to make sure the unsatisfying data records will be removed. So here is more concrete example. So you have load statement and you have filter statement. Then the field condition will be pushed into this OrcStorage. And OrcStorage can fill those data blocks which doesn't have this condition, which don't have any records of these conditions. Those blocks will be get rid of immediately. So for the data block which has some of the records of satisfying this field condition, it will load it and then pig will do the field condition again. This is how predicate pushdown works. There are some limitations of predicate pushdown currently. Within OrcStorage, we support all the primitive data type, but none of the complex data type works. So if you want to push down a condition which is on a map key, it doesn't work. So for the field condition itself, it supports the typical equal and unequal condition. It also supports between in, and it supports the logical expression such as and or not. Which it doesn't support is the is no, is not no, and match. So the predicate pushdown is not only for OrcStorage. We open this interface to all the load. So in CRA, all the load func implement this predicate pushdown interface. Pig will try to push the predicate into the loader. So that here is the interface. So basically, Pig will ask load func some information such as which fields supports the predicate pushdown and which expression the load supports. And then Pig will try to figure out if this field condition is applicable to push down into the load or not. If it is, then use the call set predicate pushdown, set pushdown predicate to actually push this duplicated field condition into the loader. So currently, OrcStorage is the only load bank implementing this interface. But when we design the interface, we also think in mind for the packet loader. So this is also in the plan. And we also introduced a logical optimizer called constant calculator in this release of pig. So if the expression, all the parameters of the expression are constant, so we will try to evaluate this expression at the compile time. So here is one example. So if you have filter and the field condition is A0 larger than 5 plus 7, then we will immediately calculate this expression and replace it with the constant 12. And here is the other example. So you have constant expression which use UDF. We will evaluate this UDF and get the result and put the result constant back. So the benefit for that is when it's obvious, so you don't have to calculate that at runtime. So you calculate it once in the compile time. So so it was improve the performance. And further, you will enable some performance improvement at the compile time. Let's see this example. So you have the field condition, which take UDF. So for the OrcStorage, for the load bank itself, it doesn't understand your UDF. In this case, at compile time, we calculate this UDF and replace that with a constant, which the load bank can understand. So we can push this, with this optimization, we can push this constant expression into the loader. So the predicate pushdown works this way. So by default, we will not evaluate the UDF, constant UDF at the compile time to make sure there is no side effect introduced. So if you want to allow the UDF to be able to be evaluated at runtime, you have to override this method in your eval func. And we did that for most of the built-in UDF and the piggy bank UDFs. And here is another implementation change in pig. Actually, this is another new feature in pig, which shift the jar, dependent jars to the backend. So before that, if you want to use some UDF store bank or load bank, you have to register those dependent jars manually inside your pig script. So think about that. We can do it better, because when you write the UDF, you know they will depend on some jars. So your load bank can tell pig, I need those jars, and pig can ship it automatically. So this is how we do that. So in the load bank, store bank, and eval bank, we provide via a new hook called get ship files. And in this, you can tell us the jars you want to you will use in your UDF. So these are the representing jars, representing class of the jar. So we will so pig will finding the containing jars for those classes and ship those jars automatically. And the other feature we introduced is jar refactory. So for those who knows pig very well, you know there is a jar called, there's a notorious jar called pig without Hadoop jar, which is a Uber jar, contains all the pig classes and all the dependency classes. So this creates a problem, especially for the downstream projects such as Uzi, because we don't publish this pig without Hadoop jar, we only publish the pig jars. to the Maven repository. So that creates some difference in when you run pig inside Uzi and you run pig natively. So in this new release, we get rid of this pig without pub.jar. We only ship pig core jar, which gives the same user experience for pig itself and downstream project. And we, for those dependent jar, we will put in the lib directory.